variable acceleration with vectors in 2 dimensions. So we're looking at kinematics, 2D motion, vectors using variable acceleration, so we have to use calculus. In this diagram, everything is in vector form, so we have position, velocity, acceleration and force, all vectors except time, which is a scalar quantity. So the position vector r for a particle is equal to xi plus yj. Now when we're differentiating, we can use this shorthand notation. So r dot, that's a vector r double dot, again that's a vector, v dot, x dot. What do these dots and double dots actually mean? Now r dot means take the vector r, differentiate it once with respect to time, i.e. do dr by dt. So r double dot means take the vector r and differentiate it twice, so work out the second derivative with respect to time, so d2r by dt squared. V dot means take the vector v, differentiate it once with respect to time, so dv by dt, and likewise x dot means dx by dt. So the dot notation is just a shorthand notation representing derivatives with respect to time. Example 1. A particle has a mass of 0.8 kilograms and its position vector is given here. Now we have to work out the velocity vector for this particle and the acceleration vector, and then use F equals ma, Newton's second law, and work out the resultant force acting on the particle. So in this diagram we start with the particle's position vector, we differentiate with respect to time, we get the velocity vector, we differentiate with respect to time, again we get the acceleration vector, we use F equals ma, we work out the resultant force. So part A, velocity dr by dt, or r dot for short. So to differentiate the position vector, we start with the I component. So 2t cubed is differentiated to give 6t squared times I, and then we take the j component, differentiate to get this, times j. To work out the acceleration vector, we differentiate the velocity vector with respect to time, so dv by dt, and that can be written as v dot in shorthand notation, dot notation. So we differentiate the vector here, we differentiate the I and j components separately. So there's the I component, differentiate that, times I. Take the j component here, differentiate, and put the j there, times j. So now we have the acceleration vector as well. So to work out the resultant force on the particle at the instant when t equals 2 seconds, we need to use Newton's second law. So F equals ma, that's in vector form, and we have the acceleration vector here, which will go there, and we have the mass already. And there's the mass, 0.8 kilograms, there's the acceleration vector, and we're just substituting in t equals 2 into here and here, like so. And then we simplify, and we have our resultant force in newtons. So once we have the resultant force worked out in vector form, we can work out the magnitude of the force. So we currently have 19.2 I newtons as the x component and 5.30 j newtons as the y component. And here is the resultant force, the missing side of the triangle, and basic Pythagoras' theorem gives us 19.9 newtons for the magnitude of this resultant force. And we have this right angle triangle because the I and j vectors are perpendicular to each other, and this side represents 19.2 in the right angle triangle, this side is 5.3. The missing side here, Pythagoras' theorem, is 19.9. For practice, try these questions.